Hello everyone, welcome to this session. The session is about distributed machine learning for digital and TV ads serving. I'm Yubo Wang, Senior Developer Advocate of AWS, and the session will be co-presented by me and Lei Wu, who is Head of Machine Learning Team at Comcast Freeview. As from the agenda, we will cover 4 aspects, including a quick AWS machine learning overview, computational advertising business in Comcast Freeview, where distributed machine learning comes in, and how cloud-native AWS services help Comcast Freeview. I will cover the first part, and Lei Wu will cover the other 3. First, let us have a quick overview for AWS machine learning for computational advertising. AWS provides a deep and broad set of machine learning services which have benefited a lot to advertising customers. Amazon SageMaker is a fully managed service to build, train, tune, and deploy machine learning models for every developers and every data scientist. I'd like to highlight 3 advantages here. First, SageMaker is easy to use. It removes heavy lifting in each step in machine learning process. Second, SageMaker can provide high scalability and performance. It can provide near linear GPU scalability to have a better performance to train a more accurate models in much less time. Third, SageMaker can reduce cost significantly in each steps, including data preparation, training, and inference. In the underlying, we have a broad set of machine learning infrastructures to support both Amazon SageMaker and customized environments. We have various GPU, CPU, FPGA, and custom chips instances, and also a lot of innovation here, including AWS Nitro Hypervisor, 100 GB network, spot instances, auto-scaling, and their combinations provide an ideal environment for better performance, better scalability, and lower cost for machine learning environments. Next, I will pass the microphone to Lei Wu for his insights and practice of machine learning in Comcast Freeview.
Thank you, Yubo. Freeview is a Comcast company, and we deliver billions of ads every day for thousands of clients in the US and Europe, such as Comcast, NBCU, Fox, Charter, Turner, etc. And we are dedicated to build a marketplace that connects both buyers and sellers. Since machine learning is more and more popular in almost all industries, so let's see how machine learning is adopted in Freeview's business. We have several products and services in our business for both brand awareness and direct response. Among all those projects and products, advertising inventory prediction is the most important one, since it lays the foundation for many other projects like client-facing, planning, and bidding strategy, etc. Technically, inventory prediction is a time sequence forecasting problem where we look back into the history and we predict the future. But in computational advertising industry, we have many different types of targeting criteria. And with the intersections of all those targeting criteria, we have millions of sequences to handle at once. And besides, in our case, we need to predict for the next 3 months on an hourly basis. And imagine this. Imagine that you are a financial analyst and your boss asks you to predict price for all the stocks in the NASDAQ market. So how are you going to solve this puzzle? Given that, we can see that we have at least 4 challenges in our inventory prediction business. The first is the curse of dimensionality. The curse of dimensionality makes our data sparse, and that in turn makes our model training even harder. The second is the complexity of engineering. Since we have to handle millions of sequences at once, training and maintaining multiple millions of models will be impractical and impossible in engineering. And besides, we need to predict for the next 3 months on an hourly basis in our case, and that sums up to 2,160 units in the future, and that's a lot. And finally, since we have to predict that far into the future, and that means we have to look back into the history for at least the same length, and that means we have to process and train on top of big data. Traditional machine learning algorithms like ARIMA can only train one single model at one time. And in our case, if we adopt traditional machine learning algorithms like this, we have to build and train millions of models, and imagine how messy that will be. So we designed a deep learning model that is inspired by the wide and deep ideology that is proposed by Google in 2016. First, we feed the intersections of the targeting criteria into a fully connected neural layer, and we call this the wide part. And on the other hand, we build a deep neural network that contains multiple fully connected neural layers, a convolutional neural layer, and a recurrent neural layer. And we can see that in this deep neural network, we have 3 branches. In the first branch, we simply input the historical sequence into multiple fully connected neural layers. And these layers will be used to extract the higher level abstractions from the input. And in the second branch, we can see that the historical sequence is fed into a convolutional neural layer before being fed into an LSTM layer. And in this way, the convolutional neural layer used to extract, convert the daily patterns in the historical sequence into weekly or even monthly patterns. So the LSTM layer on top can learn seasonal patterns from it for both long-term and short-term. And in the third branch, we can see that we create a shortcut between the convolutional layer and the final concatenation layer. And in this way, we want the output from the convolutional layer to contribute more to the final prediction. In the final concatenation layer, we can see that with the output from the left-hand wide part and from the output from the right-hand deep part, we can predict a vector with 2,160 units. And this vector will be compared with the future sequence that serves as the ground truth. The difference or errors between them will be back-propagated into the deep learning model during the whole training process. So with this artificially designed deep learning model, we conquered challenge number 1 and number 2 in the inventory prediction business case that we have just mentioned. And we all know that in TensorFlow and Keras, they provide many out-of-the-box loss functions that handle scalar values. But in our case, what we need is an element-wise loss function that generates element-wise errors and gradients. And these gradients will be back propagated into the deep learning model independently during the training process. So we designed a customized loss function to conquer challenge number 3. Since we need to deal with big data, we need different types of distributed computing engine for the different components in a machine learning pipeline. And we have several existing tools in our tech stack. And we will explain more later how these tools fit together to construct an end-to-end machine learning pipeline. This is the process that we create training samples from our original data source. First, we aggregate our transactional level data by hour to create a new dataset. And this new dataset will be sorted by hour to generate X sequence and Y sequence. Here, X sequence means the historical inventory sequence, and the Y sequence here stands for ground truth. And then we generate more temporal features like day part from the date hour field. And finally, we encode all static features to a feature vector that are marked with orange fields. Here, the Y sequence that are marked with cyan color means the training label. This fitting out version of our deep learning model helps to show where the training samples fit into the deep learning model. The intersections of the static fields are fed into the left-hand white part, while on the other hand, the X historical sequence is fed into the right-hand deep part. And in the end, with the two pieces of data ready, we can predict a vector of 2,160 units. And just like we have just mentioned, this vector will be compared with the Y future sequence, and the errors and the element-wise gradients will be back-propagated into the deep learning model during the training process. Since Freeview is running all of its business in cloud-native services, so let's see how AWS helps us to build an end-to-end machine learning pipeline. This is the end-to-end engineering pipeline, and we use Presto to fetch data source from an S3 bucket, and then the pre-processed data is stored into another S3 bucket, and then we leverage Databricks to do all types of feature engineering and data processing, data manipulations such as data cleansing, data filtering, data joining, etc. to create training samples. And with the training samples ready, we leverage Amazon SageMaker to train our deep learning complex model on top of distributed training cluster that is provisioned by Amazon SageMaker. With the trained model, the models could be either be used to do batch inference on top of multiple transactions at once, or be uploaded to a server for online serving. The reason why we use Presto to fetch our data source is because that our original data is hierarchical and nested. So we leverage Presto's built-in transformation function to transform the original data to a flattened version. And then we leverage Databricks' comprehensive operators to do all types of data processing. For example, we use Spark's windowing operation to create our X sequence and the Y sequence in our training sample process, as we have just showed before. And as you may notice that most of our tools are cloud-native managed services, and in this way, we can take advantage of the benefits of on-cloud services with ease. And underneath, we have different types of EC2 instance to support our 4 types of jobs. We split our training process into 2 phases. The first phase is called the cold start training, and the second phase is called daily incremental training. In the cold start, we try to train our deep learning model on top of big data, large volume of data from scratch. And in the daily incremental training, we try to fine-tune the pre-trained model on a daily basis with the daily increment data. And in this way, we can guarantee our model's accuracy as well as the training's runtime. And then we use batch inference to predict multiple transactions at once, whereas the online serving is used to predict on the fly in a real-time manner per transactional level. To explain why we choose SageMaker among all other competitors, we need to review our pain points as a team. The first is big data. With big data, we can no longer train a complex deep learning model on one single machine. And given the fact that Comcast Freeview machine learning team is a small team that is made of data scientists who are experts in algorithms, but not in infrastructure. So we don't have extra hands and resources to build out a distributed training cluster from scratch. And maintaining them will be more painful. And in fact, we have been suffering from the pain that we can't leverage the power of deep learning simply because we can't build a distributed training cluster. And that is really frustrating and awkward. And we all know that deep learning is dominating the play now in all industries. And the deep learning creates complex models and complex models always requires and consumes big data. And finally, we need optimal runtime performance for faster iteration. Since we need to fine-tune multiple hyperparameters during each iteration, so we need really fast iteration to fine-tune our model. After some investigation and practice with Amazon SageMaker, we found that SageMaker provides many functionalities and services for both development and production, with either out-of-the-box services or you can customize anything you want. In our case, we built out a deep learning model with TensorFlow with the Jupyter Notebook for faster development. And for production, we train our deep learning model in a distributed training cluster with spot instance. And the spot instance can be more cost efficient. And you can see that there are many other functionalities and services that are provisioned by SageMaker. So you can take advantage of those services in your business case. With SageMaker's help, we achieved our key results in two aspects. The first is model's accuracy, and the second is training's runtime. We use MAPE to measure our model's accuracy. And for MAPE, we all know that the lower it is, the better. And with traditional machine learning algorithms like ARIMA, we can achieve a MAPE with 30%. But with our deep learning model, we can get a best MAPE of 20%. And for aggregate MAPE, we can achieve a 10%, which is even better. The original MAPE here means that we calculate the MAPE on top of the intersections of all targeting criteria. And the aggregate MAPE here means that we measure the MAPE on some specific dimensions that our clients care the most. And we also manage to keep the runtime of different types of jobs in minutes level. An accurate inventory prediction allows our buyers to reach their target audience with much lower costs. And on the other hand, it allows our sellers to monetize their inventory as much as possible. And our cold start training process guarantees our model's accuracy, since the model is built on top of large volume of data from scratch. And besides, the reduced runtime of our delta training and the delta inference allows our services like bidding strategy and planning to adjust more frequently, and that is really helpful for an optimal global optimization between supplies and demands. For lessons learned, we suggest that always use Jupyter Notebook with script mod to design and develop artificially designed deep learning models. And we also found that local mod helps a lot in fast code debugging. And for cost-saving considerations, remember that SageMaker already supports spot instance ever since the end of 2019. And for inference, especially for inference on top of multiple transactions at once, I think the functionality that you need is the batch transformer in SageMaker. And for point number 6 to number 8, we will explain more later in a code example. And during your training process, you can always find different types of logs and dashboards in the SageMaker's console. And those types of dashboards will help you to monitor your training process in a real-time manner. And finally, if you are planning to leverage the power of auto machine learning, such as hyperparameter tuning, auto algorithms selection, etc., you don't have to build new hills from scratch, since SageMaker already supports such auto machine learning functionalities with autopilot. This code example shows how easy it is to develop on top of Amazon SageMaker. The only things we need are 4 pieces of code. In the first piece, we simply import SageMaker and its libraries, just like we import NumPy and Pandas in our Python script. And the second piece requires more attention and focus, since here we define a TensorFlow estimator with multiple parameters. First, we tell the estimator where our training code is with entry point. And secondly, to tell SageMaker that we want a distributed training cluster, we need to specify two parameters here, and that is instance type and instance count. And with that, SageMaker will help us to launch those numbers of training servers automatically. And thirdly, we simply set the script mod to be true. And by default, SageMaker will save our trained models onto local storage. So if you are planning to store your model to a S3 bucket, you need to change this output path to a S3 storage location. And for cost-saving considerations, don't forget to change the use spot instance parameter to be true. And finally, if your job runs more than 2 hours, you may want to change this max run value to a bigger value. And with the estimator defined ready, we need to tabulate where our training data is in the third piece. One thing to notice here is the distribution mod. The default fully replicated mod will make every training server to download the full copy of the entire dataset, and I don't think that is what you need. So if you want a real distributed training process, you need to change the distribution mod to a sharded by S3 key. And finally, in the last piece, the only things we have to do is to call the estimator's .fit function on top of the inputs that we have just defined in the last piece. And that's it. That's all we need to train a deep learning model on top of distributed training cluster. And with SageMaker's help, we reduced our overall efforts by 60%. And we also managed to reduce our on-cloud costs by more than 50%. And we also got improved efficiency and enhanced flexibility. And with that, we conclude our presentation today. Thank you very much for your time.